just take a little side note here to the reduced mass correction. The reduced mass correction is kind of cool because it's not just about the Bohr atom. It's about any orbital, any orbits. All orbits occur about the center of mass of the system. And whether we're talking about the moon going around the Earth around the sun, or the electron around the nucleus, you really, in order to be more precise, while you can assume one thing is sitting still, you can assume the sun is sitting still and the Earth is going around it, it's more precise to do what's called the reduced mass correction, or take into account the fact that they both orbit the center of mass. So let's exaggerate that a little bit and see how it works. Let's say that this is one mass, big M, and another mass, little m, and that they orbit something, right? In most cases, when you're talking about a large thing orbiting a small thing, the center of mass is going to be really close to the center of the larger mass. I mean, when you're talking about the Earth and the Sun, for example, figure out the difference between the center mass. Why don't we? Why don't we? All right, let's just go ahead and do that. Aside, center of mass. Center of mass. If the Sun has a radius, I don't know how we know this. Maybe we had an alien go up and measure it, but the sun has a radius of 432,690 miles. I don't know if that made sense. Having an alien go measure it. We asked an alien who had gone to measure it because we haven't been to the sun. I don't know who got a tape measure large enough. But anyway, so that's the radius of the sun. How far away from the sun are we? At least on average. Okay, here are some numbers. Okay, the radius of the sun, 6.934 times 10 to the 6 meters. The distance between the sun and the earth, 1.4849 times 10 to the 9th meters. The mass of the earth, 5.972 times 10 to the 24th kilograms. Mass of the sun, 1.989 times 10 to the 30th kilograms. So let's go ahead, right? So the center of the sun is at the center of the sun, right? It is I don't know exactly what I'm trying to say, but let's figure out the center of mass of this system, the center of mass of the system. So let's go ahead, and in order to find the center of mass of the system, let's put my coordinate axes at the center of the sun. So let's put my coordinate axes at the center of the sun and say that in this coordinate system, the position of the sun, x sun, is equal to 0, and the position of the earth, x earth, is equal to 1.4849 times 10 to the 9th meters. And that's all we need to know. The center of mass, the position of the center of mass, is equal to the mass of the sun times the position of the sun plus the mass of the earth times the position of the earth divided by the total mass of the system. Right, where you should remember things like this. These are basic physics. And so the position of the center of mass, if it is 0, then the center of mass is at the center of the sun. But it can't be 0, right? It can't be 0. The center of mass of two objects that are separated by distance is never going to be at the center of mass of one of the objects. Look at the formula for center of mass. That's not possible. But it may be close enough that we can assume, for all intents and purposes, the center of mass of the system is at the center of mass of the sun. But in reality, depending on how carefully we want to make our measurements, we should never assume that. We can assume it in a lot of things. It's fair to assume it. But in reality, it's never going to be at the center of the sun. And the result of that, remember, we've talked about this before, the result of that is what allows us to discover planets going around other stars, knowing that the fact that if a star has something orbiting it, then that star will be going around the center of mass of the system, which is not its own center of mass, so the star is going to have a little bit of a wiggle to it. And that wiggle allows us to predict what is going around it. Okay, anyway, let's go ahead and finish this calculation. So I'm just writing on the same page at the top. We can go ahead and plug those numbers in to the center of mass. And the result is that I put an intermediate mathematical step here, that the mass of the Earth is so small compared to the mass of the sun that it is insignificant to the number of significant digits I've got here, right? The significant digits are 4 or 5, and that is in the 6th significant digit of the mass of the sun, or the total mass of the product, total mass of the Earth's sun. So there you go. It's kind of a interesting result. 4,458 meters. So the center mass of the system, I couldn't kind of giggle because the center mass of the system is so close to the center mass of the sun. I mean, the sun is 6.9 million meters in radius, and the center of mass is only 4,000 meters from the center of the sun. So it is, what is that? 1 part in 1,000. It's 1 part in 1,000. So it's still not, it's not entirely insignificant, right? 1 part in 1,000, right? Yeah. 1,000 times 4.458 gives us 4.5 million. So it's a little less than 1 part in 1,000. 1 part in 100 of 1%. So it's a 0.1%. So it's about a 0.7% correction. 0.7% is not insignificant, right? It's not insignificant, but the center mass of the system is pretty darn close, and certainly, right, it's 1/1000th of the distance from here to here. The center mass is 1/1000th of that different distance away from the origin. Okay, so the center mass is still pretty close to the center of the sun. Okay, so let's look at what this reduced mass correction does for us. We haven't done the reduced mass correction yet. We were just finding the center mass of the system, just to show that it is not at the center of the sun. And in order to take that into account, we need to do what's called the reduced mass correction. Okay, so let me exaggerate that center of mass out, or just say that they're closer in mass to each other, so that center of mass is not on top of one of them, so I can show how this works. And say the center of mass of the system is as shown. That means that the larger mass, right, is going to orbit around that center of mass with an orbital radius of r1. The smaller mass is going to orbit around that center of mass. I don't know if I'm drawing these terribly accurate orbits, but with a radius of r2. Right, so this is going to be, this is r1, and this is r2. That's what I'm trying to show. Not terribly well drawn, but that's what I'm trying to show. In this particular case, these two are orbiting, I was talking about planets, but this could be an electron. This doesn't change. The argument doesn't change with an electron going around a nucleus. It's just that the force that's making them orbit is the electromagnetic force, or the Coulomb force, as opposed to with planets, it's the gravitational force. They both have the same form, right? That the force between these two objects, the force that one exerts on the other, is G capital M little m over the distance between them squared. Or if they were charges, the force between the two objects would be K Q1 Q, or big Q little q. Instead of Q1 Q2, we could just do big Q little q over r squared. Exact same form. So the reduced mass correction doesn't change whether we're talking about orbits because of gravitation or orbits because of Coulomb force. The reduced mass correction still holds. Okay, so let's see how it works. So let's just assume that the force between these two things is gravitational, so that the force between them is Gm1, or the force on any one of them is Gm1, G big M little m over r squared, and they both go, but the orbit they go in is an orbit not of radius r. They go in a radius of r1 or r2. So that is going to be equal to m little m v squared, the speed of little m. Let me try that again. Little m v little m squared over, and little m has a radius of r2. mv squared over r. Sorry, it's the centripetal force, or big M v big M, trying to differentiate between these, over r1. But we can show that that is equivalent to something going, so this one has got a radius r2, this one's got a radius r1, right? We can show that that's equivalent to, let me go back to the other color. One minor error here, which is that the relative acceleration is that, and so if we write them in terms of magnitudes, because one of them is always going to be accelerating that way and one's always going to be accelerating that way, one of them has a minus sign, so the relative acceleration is that. The relative acceleration is, I think I already talked about this. So if I'm sitting on big M and I'm looking at little m go around me, I'm sitting still. So this is correcting from looking at the center of mass point of view to looking at the sitting on big M point of view. And we have a relative acceleration, v over r, plus, a relative acceleration of the difference between the two accelerations. One is negative, so we have to sum v little m over r1. I'm sorry, v big M squared over r1 plus v little m squared over r2. And they have a relative speed of v and a relative distance of r, so that sitting on big M, little m is moving at a speed v relative to me, and it's a distance r away from me. So note that, read that from the top, that the gravitational force is gmm over r squared between the two on any one of them. Therefore, the acceleration of big M is the gravitational force divided by little m. The acceleration of little m is the gravitational force divided by big M. And the relative acceleration is the sum, is the magnitude of those two, the sum of those two magnitudes. So the relative acceleration is going to be as follows, as shown. And that relative acceleration is v squared over r. And it is the speed that sitting on one of them, the other looks like it's moving, divided by r, not the speed relative to the center of mass, which are v1 and v2, or v sub m and v sub m. And so therefore, f sub g is equal to little m big M over m1 plus m2 times v squared over r. In other words, right, g little m big M over r squared equals little m big M over m1 plus m2. Sorry, m1 plus m2. This is little m plus big M. I changed. I probably should have done that to differentiate them from the beginning. So what this tells us is that if we're sitting on, right, so the center, from the center of mass, point of view, right, from a non-relativistic point of view, not relativistic as in relativity, but from sitting still in the universe point of view, pretending that this is a cm is a stationary point in the universe, we get this. But if we instead put ourselves in the frame of reference of big M, the orbit looks, the other mass orbits me. So if we can assume that big M is sitting still, the other mass orbits me with, as if it's got what's called a reduced mass of this. Little m big M over the sum, the product over the sum of the two masses. So again, what I'm trying, I'll say it one more time because I feel like I haven't been terribly clear. If we pretend that the universe is a fixed reference frame, and we're looking at a real orbit from the center of mass of two masses, they both go around that center of mass. But if instead we want to say, but relative to one of them, if we sit on the larger mass and we pretend that's our stationary reference frame, or that is our new stationary reference frame, the smaller mass goes around us, but the motion is described by Newton's second law as if it has a smaller mass. And the smaller mass is the product of the two masses divided by the sum of the two masses. This is called the reduced mass formula, and it is typically given the Greek letter mu for reasons which I don't know, but that is the reduced mass. I think that's pretty interesting that we can do that kind of correction in order to properly describe the Newton's laws and motion for two things orbiting each other. There you go, reduced mass.